Okay, AP lecture. This is about angular speed and angular acceleration. Notation: omega is angular speed in units of radians per second, and alpha is angular acceleration in units of radians per second squared. Linear equations: x position final is equal to x position initial plus v sub I t plus 1/2 at squared, and it is similar to and associated with theta final minus theta initial plus omega I t plus 1/2 alpha t squared. And those are equation 7.8. 7.7 says velocity final is equal to velocity initial plus at, which has associated omega final plus omega initial plus alpha t. And as we're talking about things going in a circle around a center, we have an initial position in theta, and a final position in theta. So that's a delta theta. This is an arc length called S on the circle from theta I to theta final. So theta final minus theta I is delta theta, which is 7.2. And that delta theta is the arc length divided by the radius. So suppose we go one complete revolution around the circle center, then that's 2 pi r divided by the radius, and we get 2 pi, which would be delta theta in that case. Now the average angular velocity is omega average, or we can put a bar over it and that would be average, is theta final minus theta initial over delta t, and that's delta theta over delta t, equation 7.3. So instantaneous value of omega is the limit as delta t approaches 0 of delta theta over delta t, equation 7.4. And we know that counterclockwise direction is considered positive, and that you need to understand and know as well. Now, the average angular acceleration is alpha average, or alpha with a bar, omega final minus omega initial over delta t. So delta omega over delta t, that's equation 7.5. And instantaneously, alpha is equal to the limit as delta t approaches 0 of delta omega over delta t, equation 7.6. Guys, you've got to make sure you make your omegas look like that and not that. I don't want to see it written incorrectly, because I will take points away. Now, a rotating body that's rigid, for example, my pencil, if I turn it like so and keep it at a constant rate of turn, then every particle of that body possesses the same angular speed and the same angular acceleration. So we could talk about the tip, we could talk about somewhere in here, somewhere, and at the very center of this rotating object, of course, the center is rotating, but the center is not in translational motion. So now we have an additional equation we have to talk about. Linearly, the final velocity squared is equal to the initial velocity squared plus 2 times a times s. This is the translational delta s. Okay. So it's similar to omega final squared plus omega initial squared plus 2 alpha delta theta. And this is the displacement angularly, displacement linearly, equation 7.9. And so here's your assignment. I need you to read examples 7.2, 3, 4, and 5. Understand those explicitly. And then your assignment is 7.1, assignment 7.1, colon 1, 2, 3, 7, 9, and 10. You may work together at the tables on these. These are due at the beginning of class tomorrow, or they can be due once you finish today.